Hello. Thanks everyone for being here. So my name is Hongyan. I'm a principal engineer from Trenton. Sorry, hello. Yeah. Hello. Hello. Maybe I have to stay away from the microphone. I can just yeah.
Have you tried turning it on and off again?
Yeah. I'm from Trenton. This is a mobile phone, smartphone company. Maybe you guys haven't heard of it. So it's a relatively small company compared to like Apple or Samsung, but we only captured only 50% of the market share in Africa. So yeah, that's a very small company. Yeah, so I'm also ex-ARM, so it's nice to see a lot of familiar faces here. This topic is about using AMU PMU, mostly in CPUFreq for power efficiency. I think people are familiar with schedutil, especially in its role in guiding CPUFreq. The problem is that mainline CPUFreq is pretty generic. It's basically based on the idea that performance is linearly proportional to frequency. If you get double the frequency, you get double the performance. But we all know that this cannot be true. And we have some questions like, does high frequency really give you high performance? And is the scaling really linear? Or finally, is CPU frequency even the bottleneck of your workload? So also some background why we are investigating this. The first is that when we benchmark different workloads, we found that, of course, in some workloads, the CPU capacity is almost perfectly linear, like some ALU heavy workloads. But in some other workloads, like a big matrix multiplication, like the graph down below, after you reach a certain frequency, like on the x-axis, almost 2.6, 2.7 gigahertz, your performance just stops growing. And the bad thing is that it's completely workload dependent. We do have some help from vendors, like we use MediaTek SoCs, so we have some help from them. And we ask them, can you come up with something? They give us something like called nonlinear capacity model. It's basically, it's kind of two linear frequency ranges pieced together. So in the beginning, performance versus capacity is growing very fast, and then it grows very, very slowly. But the thing is that not all workloads behave like this. Sometimes it's still linear, like the first graph, and sometimes it's not. So we have to dynamically decide which one is it. And the reason the reason why we care so much about the power efficiency here is that in some emerging markets like in Africa, the limitations are very, very different. For example, sometimes you cannot expect the customer to charge the phone every day. Sometimes their power network is not that good. So they really care about power efficiency. We even have some engineers that tune each app. For example, in some apps, they find that applying some frequency ceiling almost doesn't hurt performance at all. So they do this app by app. And of course, this is completely not scalable. So they ask the kernel team, can you come up with something that automatically identify like this workload won't benefit from high frequency. And so you can actually drop the frequency to some extent. Yeah, so this is basically repeating what people just see in the previous slide. So like we have some micro benchmarks. So matrix 16 is basically a tiny matrix, adding two matrices together. Very straightforward. In this part, it's basically in the L1 cache. It's not even stressing, it's just ALU and L1 cache. So the performance is completely linear, but matrix 256 Hadamard multiplication. The stress is multipliers and memory, and this is 256 is actually a 3D matrix, 256 by 256 by 256. So it's even outside the L3 cache, it's even outside the SLC, it's mostly in DRAM. So the stresses multipliers as well as the memory channel. But the thing is, schedutil simply doesn't know what's going on here. So for these two, as long as these two workloads are running, they look like the same to schedutil. Oh, you're running, you are always running a task, or you have the same duty cycle, so you look completely the same to me. But the thing is, for the second workload, there's clearly the need to drop the CPU frequency, because CPU is not, at least in this micro benchmark, the CPU is definitely not the bottleneck. So if schedutil doesn't know what's going on, so we then need to teach, we need to teach, in this example, it's only CPUFreq. We need to teach CPUFreq. Please try to understand what the workload is actually doing and see if you really need to raise frequency, or you can drop the frequency here. Yeah, actually we can though, because we have, at least on ARM64, we have a lot of micro-architectural counters. There's AMU, and there's also, if AMU is not enough for you, then there's also tons of PMU counters for you to use, and there is also perf framework in the kernel. So what we do here is that we do statistical analysis. Actually, some other vendors try to do the same thing, but what they do is they try to guess which one is the best AMU PMU counter, which one is the best. For example, maybe IPC, which is cycle and instructions, these two counters. They first guess, oh, maybe IPC can help here. Maybe IPC, a low IPC means I can drop frequency. A high IPC means, okay, performance scales linearly. First, they try to guess. And then they do some benchmarks. And then they find, oh, maybe this is not the best to use. And then they guess some other counters. And then they do that, repeat the whole process again. Of course, we're a small company, and we really don't have that many engineers to brute force the way into this. So what we do is we simply run all these micro benchmarks. So some of the benchmarks are ALU heavy, TLB heavy, or memory heavy, some matrices, and some simple multiplication. We try to cover all the parameter space. And what we do is that we just collect all the counters, not all the counters, but like a lot of counters, like 10 or even 20 different counters that we think that is like relevant to what we're doing here. So we don't just pick one or two, we just collect as many different counters as we can. So I'm going to give you, actually, this is only part of the data we collect. We have so many different spreadsheets. But this is the data that we collect from Dimensity 8400. It's basically, and also this is a pretty good platform for us to do some research on, because there's only Cortex A725. All the 8 cores are Cortex A725. So it's basically eight cores of the same CPU. And the only difference is the max frequency and also some L2 cache size differences. But they are the same CPU, essentially. So we try to pin our micro benchmark on the CPU. And then we try to scan the frequency from the top frequency to, actually, it goes down to the minimum frequency. We run the micro benchmark. I think we run it 20 seconds or 10 seconds each time. So it's basically a fixed time window. And then we measure how many instructions it actually completes at different frequencies. So it's basically, if you complete more instructions, then the performance is higher, because yeah, they all run within 10 seconds. And then we collect all the different counters, like the memory stalls. This is ARM64, so the counters may be different from x86, and the L1 Dcache, L1 Dcache accesses and refills, L2, and also some derived counters like IPC is basically cycle instructions, divided by cycles, and the stall percentage basically is stall mem cycle divided by the total number of cycles, and L1D some of the derived metrics. So this is an example where performance scales almost perfectly linearly with frequency. So you have, if you have 20% more frequency, you have 20% more completed instructions. Yeah. And there is another example, which is in some of our benchmarks. For this one, it's I think it's a big matrix, even outside the size of SLC and L3. What you see is that even at 2.6 gigahertz, we pretty much still get 99% of the performance at 3.2 gigahertz. So this tells us, at least in this micro benchmark, there's almost no point, at least unless you really care about the last 1% of the performance. At least in this micro benchmark, if you run it at 2.6 gigahertz, it's pretty much the same as 3.2 gigahertz. And we also profile things that give us linear scaling. We also profile, like we sweep the entire parameter space, and we also profile things, workloads that give us like this kind of nonlinear scaling, which plateaus at some frequency. Okay, so we get all the data, and what we do next, actually this is a giant spreadsheet with all the different counters and the different frequencies, so I'm only showing part of it. Okay, so next is how we actually do some statistical analysis. So our method of doing analysis is whenever we see that a lower frequency is sufficient, like that, this spreadsheet, whenever we see that you don't need that high frequency, we simply mark that we change the label from 3.2 gigahertz to just 2.6 gigahertz. We keep the original frequency, but we also, like we have some engineers to label the data. At 3.2 gigahertz, you don't need 3.2. You don't, like 2.6 gigahertz is good enough. And then we kind of relabel the real frequency versus the frequency we think is good enough. Yeah, sometimes we have like a margin. For example, if like for this one, we only like get 99% of max performance. Sometimes we say, okay, we drop the a little bit more. Like if you get 98% of the max performance, then yeah, we use that frequency instead of the higher frequency.
Is your performance anywhere indicated here?
In the completed instructions, the number of completed instructions, because yeah. So we do this. So we then have a vast amount of data with labeled frequencies that we think are good enough. And then what we do next? Yeah, it's basically what I just said here. That's this slide. And then what we do next? Actually, what we immediately realize that this might be a perfect task for a neural network. So yeah, you just feed the data into neural network, and then it will tell you with the proper mathematical skills, which I probably don't have, or to tell you which counters are the best counters to indicate when you can drop frequency, which counters are probably irrelevant. But our first attempt, actually, we only started this, we only got the request from the performance tuning team only several months ago. So it's very early in the research phase. We think maybe we start with a neural network, maybe that's an overkill. So we start with something very simple, linear regression. It's basically, we assume, maybe this assumption is not even the best assumption, but at first we assume that the counters can affect how much frequency you can drop in a linear way. For example, if you have double the memory stalls, counter memory stalls, then you can probably drop double the frequency. So that's our initial assumption, which I'm pretty sure is not perfect. That's where we just start from. And then we use linear regression. And then we try to pick which are the most important counters that we should use.
IPC, only IPC.
I will get there. Actually, I even put it into counterintuitive because we found that it's not that good. Sorry.
All your stalls are in IPC.
But yeah, I would get there. So basically, we use stepwise regression. So we add counters by counters. So let's start with no counters. Then you have no idea how to what to do, and then you just use one counter. If you use one counter in the linear regression, there is also R squared. The higher, the better your model fit, your linear regression model fit your data. So we just use one counter, and then we pick the counter. When we add the first counter, we pick the counter that increases R squared by the most. And then we add that, and then we pick the second counter. I'll probably just give you an example. For example, if the first we use IPCN metric, and we found probably if I use memory stalls, R squared is maybe 50%, and then if I use IPC, it's only 40%. So the first counter I will add is actually just memory stalls, because as the first counter, it beats all other counters. And then I add the second counter, which increases R squared the most. I do this step by step, which is just called stepwise regression. Yeah, we add the counter that increases R squared the most at each step. Yeah, that's basically it, actually. A linear regression, there's not too much to say about it. It's very simple. And we might, as we iterate our algorithm, we might even eventually abandon linear regression, but this is what we're doing as our first step. Actually, I should probably do a guess game here. So at least in our study, which ones do people think are the best counters, which ones are the worst? So the intuitive ones, stall back and mem. So this is an AMU counter, which is very low latency. And it describes, maybe ARM colleagues can also correct me here, it describes in the L2, between L2 and L3, because I think in ARM CPUs, normally CPU L1, L2 are in the same frequency domain. So the stall back element describes this frequency, how much this frequency domain is stalled by L3, actually. So this is quite intuitive. If this counter is very high, it means that your the CPU, because the CPU frequency domain, the CPU plus L1, L2, is actually stalled by the L3. So if this number is high, you probably don't need to keep yourself at the max frequency. And also the L2D cache refill, there's some kind of overlap between these two, because yeah, the first one is describing the number of stalled cycles. The second is basically describing how many refills are there between L2 and L3. What we found, interestingly, at least in our study, IPC is not that good. Very interesting. IPC is not that good. IPC might be good in the same workload. For example, if you are running the same app, and then IPC is high, it means, okay, now the stalls might be low, and if IPC is low, maybe the stall is high. But across different apps, a high IPC, a low IPC does not mean it's stalled on things, on other components.
So yeah, differential.
Yeah, for example, like divisions. Divisions usually have very low IPCs, but it's actually stalled on internal CPU ALUs, not on outside things. And we found that even within the same map, it's not, IPC is useful, but it's not as good as the stall back and mem and L2D refill, at least on ARM, sorry.
How many workloads did you use to train your model over here?
We have many different benchmarks. They are all actually now, at this moment, they're all micro benchmarks. Some stress ALU, some stress memory, and they all have different memory bandwidths.
All synthetics.
Yes. Because the problem we have is that synthetic, you can measure performance very easily. I can just run it at a fixed amount of time and measure a number of complete instructions. For real workloads, yeah, it's kind of a bit difficult, but you can do that, I believe.
So, are you scaling the tree cache in your current implementation?
Yeah, that's a very good question. Ideally, if you do this, your L3 cache, for example, if you want to drop the frequency, if you measure all the spreadsheet, the data, you should keep the L3 at the same frequency. And actually, this is ideally this kind of linear regression, this method should be used on SoCs where you can independently control L3 frequency. Sadly, on MediaTek SoC, it seems you can control it, but then some numbers we look, oh, they don't look ideal. It seems even if you can control it, there's still, at least on MediaTek SoCs, there's still some correlation between CPU frequency and L3 frequency. So I have to, actually, it's on my final slide. The caveat is actually we are doing this study on a non-ideal platform. So if you can control the L3 frequency, that's the best platform you should use. Right. Okay. Next is we're going to train a linear regression model. And then with the parameters we get, with the linear regression coefficients we get, we then feed it into CPUFreq. And then CPUFreq, if it finds that it's mostly linear, so the frequency, the amount of frequency you can drop is proportional, linearly proportional to backend memory stalls and L2 cache refills. And we try to apply this to a couple of apps on our phones. The first one is Geekbench. We find that it behaves really well in multi-core. It pretty much doesn't degrade performance, multi-core performance, and you save almost 8% of CPU power. That actually not CPU power, but CPU, but the entire phone power without display, without audio. So it's not the same as SoC power. But in single core, we find that if we do this, yes, the power is dropped by quite a lot, almost 20%, which is kind of scary. But the single core score is also dropped by almost 5%. So it's not ideal, but actually it's power efficiency wise, this is pretty good. But still in Geekbench, you probably don't want to drop almost 5% of the score. And yeah, we have some ongoing study on how to do this. Maybe some trade-offs between power efficiency and performance. The next one is Edge Gallery, which is actually a Google app. They're trying to put some device LLMs on smartphones, and this one is a CPU LLM running entirely on CPU. Actually, for this one, it's pretty interesting because the number of tokens per second. So this is an LLM, what we are benchmarking an LLM with 4 gigs of occupied RAM. So the number of tokens is dropped by 4%, but it's the power is dropped by more than 1 watt, actually. And this is unlike Geekbench, where people care about the absolute performance. This one, if a customer sees there is a 4.2% drop in the number of tokens it spits out, I don't think anyone will notice. But actually 7 watt versus 6 watt, that's actually a big gap. Above 5 watt is already, the temperature will already rise pretty quickly. The 7 watt is like, no, the customer won't accept it. 6 watts is like, maybe I can tolerate for maybe 10 seconds, 20 seconds. So it actually, in terms of power consumption, it makes a big difference. So yeah, if we apply our model to this app, yeah, it's pretty good. The next one is also a mobile game where people play a lot. And this is a very CPU intensive. Of course, it's also GPU intensive, but in some other games, it's only GPU intensive, but this one is also a bit CPU intensive. If we apply what we just did, we apply our model, the FPS is basically, I would say, it's in the error, statistical error territory. The 59.41 is FPS, and on the right-hand side is the standard deviation. We dropped the FPS by a little bit, increased the standard deviation by a little bit, but there is a, I would say, a quite significant average power reduction. And this is the, actually, this is the whole smartphone power consumption without display, without audio. If we just look at the SoC, maybe percentage is even bigger. So that's, we already put what we just did into these apps. Okay, that's pretty much it. But like I said, this is only beginning of actually the large project. We do have tons of questions we want to answer as our project is going. The first one is a linear regression. It's probably the simplest regression you can do. Anything is probably better than this. Like a tiny machine learning model is probably better than this. And some of the parameters is probably not linear anyway. For example, L2D refills, it's usually behave like this. So if it's under some threshold, your L3 can keep up. If it's above some threshold, suddenly L3 cannot keep up anymore. So it's not a linear relationship. So maybe what you should do is to do some proper machine learning models instead of trying to capture everything in linear regression. Some performing certain workloads also there are still some bigger regressions than what we want, and we are still investigating why they're doing this. Maybe ask ARM to give us better counters. So ideally, a counter, if the counter is 0, it means I can now, if I increase frequency, I get proportionally better performance. And if that counter is 100, it means, okay, your CPU is completely blocked by something else. Then don't increase frequency anymore. It won't help performance. And if it's in the middle, like that counter is somehow between 0 and 100, then it means, yeah, you can get more performance, but not proportional, not linear proportional. Like, actually, the stall backend mem, the ARM counter, it works really, really well. But it's still, there is a gap between that and the ideal counter that can tell us this information. Oh, and also I didn't mention the whole thing because we only did this for only a couple of months. The whole thing is only per CPU tracked. If you have 2 tasks that are alternating on the same CPU, one is stalled on memory and one is only ALU intensive, you are getting an average, so you are hurting the ALU task, and you are not saving as much power as you can for the memory task. So maybe we should, instead of per CPU tracking, we should do both per CPU and per task tracking. Oh, and the next one is, I'll first talk about the complete automation. So actually the whole thing, there's nothing really that needs to be done by a human being. So you should just have a script that runs all the benchmarks and get all the data and try to do linear regression, or in the future, if we have our model. There's nothing that essentially needs to be done by humans. So can we do this completely in the script? And also, yeah, there is another, which is kind of maybe even outside this topic a bit, which is, do we simply want, maybe not schedutil at this moment, but simply CPU-free? Can we design CPU-free? And the input is only pretty much just counters, maybe per CPU per task. Because if you think about it, some of the information you get are from architectural counters anyway, or micro-architectural counter anyway, like time. They are from some counters, you translate into the timestamp in the Linux kernel, and then you use that to feed into some health tracking, some other kind of like vault in mobile devices. Essentially, you get these information from counters anyway. So why not just use counters? We train a model. We simply feed all the counters. We don't feed like PELT signal or util number or some other numbers. We just feed counters and see if we can train a model with train a good CPU-freq model. Yeah. Actually, that's everything.
So if I understand correctly, what you're doing is that schedutil in your test, schedutil receive a value from the scheduler, and you adjust that in schedutil according to the counter, the real frequency that you need. Is it correct?
Yeah, well, actually, we still use schedutil frequency, but in the final step, in the final step, we see if we can drop it by a bit.
And that is just a unified model running across all the 3 workloads that you showed. You're flipping the model between the workloads, right?
No, yeah, it's one model.
And how many counters did you use in this instance?
Actually, I think just
those 3 that you mentioned?
Yeah, I think just 3. The cycles instructions. Oh, no. Cycles. Actually, we don't even use IPC. We only use 3 cycles and memory stalls and L2. Yeah, we just use these 3. Yeah.
So yeah.
You are talking about instructions instead of cycle counter. Otherwise, you don't have the stall percentage. Percentage is for instruction, how many cycles installed for this instruction. So instruction counters and the stall counters, then you have for this percentage.
I mean, ARM64, the stall is a cycle count. So it counts how many cycles are stalled on like L3. So it's essentially another cycle counter.
But you will, okay, then you will not get the workload type. For example, the same instructions, how many workloads, or which type of these workloads will be?
Yeah, at least in our model, you can, at least the 3 counters we use is basically telling you, yeah, how much your CPU is stalled by L3 and other things. It doesn't tell you other things.
So I think the counters also affects what's the architecture like. Do you have an independent frequency can be independently scheduled for your L3 system cache and memory controller, and also the NOC bus side, for example.
Yeah, that's actually that's the ideal platform we should use. We should have used. So if you have different frequency domains completely independent, then it makes sense for you to drop frequency. What we found that is that sometimes when we drop the frequency, also the L3 seems to also drop frequency. And this is a big headache for us. So sometimes in some, and this is, actually we're doing this in a non-ideal platform. Ideally, you should, you should completely control L3 by yourselves and also DRAM by yourselves.
So the fact that your L3 is dropping or scaling with it's a known issue that the voltage domain of the electric gas is shared with some other CPU.
I think on MediaTek they have this weird thing. I don't think like it's only slightly tied to CPU frequency. It's affected by some also other things. You can control it, but yeah, it's like the numbers you send to L3 might not be the final L3. They are still they are doing some weird stuff which they don't want to tell us, which is not good. But ideally, yes, you should. If you want to do this, ideally the platform you should use is a platform where you can independently control all the frequencies. Yeah.
So we cannot redesign schedutil for this because it needs to be cross-architecture.
Yeah.
And then, as far as I'm from the AMU is a non-configurable counter set that is read-only.
It's a free running counter, but you can pick the event.
It's still configurable.
Yeah, there's some level of configuration.
So then you're gonna be contending with other people that want a PMU. And on your phone, you might know you are the only one, but we cannot in general consume PMU resources.
Yeah, that's
people would be upset.
You're allowed AMUs in the kernel, but not PMUs. AMUs are for
phone users.
I use AMUs.
This is an old discussion.
Yeah, actually, that's the very reason why we try to pick which counters matter most in the very beginning, because in some of our phones, there's only 4 PMU counters, and some of them are used by MediaTek, of course. They want to do everything. And then there's only like 1 or 2 left for us. But that's the exact reason why we do that. We want to pick and then why we only have 3. Actually, the overhead is reading 3 counters. The overhead is like it's not that much. It's simply because we don't have that many PMUs left. Yeah, I will see that's definitely a problem. We are not going to, at this moment, we are not going to push it to upstream, because this is highly, at least at this moment, what we do is highly ARM specific. What we're trying to do here is just to show people the results and see if maybe on x86 people do the same. Sorry.
Instead of doing that in schedutil, have you tried to, so in PEP, we are already using the AMUs to define the utilization. So maybe that will be easier.
Yep.
With all this PMU to, I mean, to give a number of cycles, which will. Sorry.
You can do it in driver, though.
Yeah, you can do it in the driver, but regardless, so Intel had the classification thing at some point. Did that completely go away, or is that still?
It's still there, but it gives you a number, a final answer to your question of what are you doing. Instead of having you looking at every single counter, it doesn't work for you.
Right, but yeah, so being able to classify tasks either through user space interface or with some help is something that we might be able to look at. But yeah. Other than that, we all know that the linear thing is wishful thinking.
Yep.
There's no discussion there. It's just,
One more question. Did you compare? Because I'm wondering what is the benefits coming from? Did you compare your implementation with symphony capping the frequency?
Yeah, we actually do have some engineers that brute force the way into this. Sometimes they just cap the per app frequency. They just try to cap the frequency more and more until it hurts performance by a lot. Actually, if you really have the time and engineer resource to do this, eventually you might get similar results actually. Provided that your workload is kind of static. So for example, in the CPU LLM example, if you have the engineer to actually slowly tune the frequency cap, you can get the similar results. But the thing is, that's a very memory heavy workload. But if you have other apps, sometimes it's memory heavy, sometimes it's not. Then yeah, this works better than that.
My question goes in the sense that whether the user will notice if you cap it 5% and you 15%, and then it is noticeable by the end user.
At least what we.
Because you can have a benchmark number, but people in the real world, your customer will not.
Yeah. It's at least for us. Yeah, we are not enable this in all the apps. We have this. You can enable it in maybe a lot of apps, but not in all of them, because we have this like in the vendor, like in companies like us, we have the testing team. They need to evaluate your idea before they put it into the final product. If they see that you are actually affecting the performance of this particular app, they will put it in a deny list or whatever. Yeah, we hope it could be a universal idea, but yes, there are still outliers sometimes.
Yeah, because as Peter was saying, we also look at this, and it gets complicated very quickly. So a simpler solution gets the job done. It's very useful. That's why it was simply frequency.
Yeah. Yeah. To be honest, sometimes if you have the engineer resource to do this, you might get the same benefit.
So I have a question. So what we are missing to get it upstream? Is it an AMU framework? So AMU are free, at least those which have been used. Maybe
I think
Refil is not there, right? So that would be a counter from AMU. But do you have the non-blocking framework to get those in driver layer? Or so
I think
that no go for the schedule.
Yeah, I think the biggest
opinion was to go to the driver.
Yeah, I think the biggest problem I see is that you have to profile the different SOCs. It's like an energy model, but like a linear regression coefficient model. Yeah. You have to load that for different SOC. You need to load a different one, and then maybe you can upstream a framework like this and let the user do that. Load different models.
That's how we get the energy.
Put that into the firmware and
Yeah, maybe.
For where, fine tune things.
But
Like
if
the
it's in
LP
the
code
driver
stuff.
code, can we just get the DT or something to set this up?
And also the question also is whether linear regression is the right thing to do anyway.
Well, that will be figure out later. But so the results are promising, and the mechanism looks like it will be more dynamic than the static configuration to find the capping OPT, because you can change that after a while when you switch the context on the foreground on your phone. Then sooner or later you will pick up the new pattern from that app, right?
Mhm.
And then looking at the Geekbench result, there are different flavors of those subtests. Some of them, I bet they will they will get the highest frequency, and some of them they will benefit from this reduction, and they will reclaim the power budget, maybe even for the next run. That's why you get a nice score. So it is picking up some patterns, and it reacts dynamically. But now you have modified schedutil, right? Not the
Actually, just CPU-free part, not really. Yeah, for task placement, we didn't do anything. Yeah, we just get the frequency and see if I can drop it, like reduce the frequency, and then that's pretty much it.
Okay, so that was in the shim layer in the CPUFreq framework.
Yes.
Okay.
So where do you put it code specifically between the governor and the CPUFreq, or between the driver or inter-driver race?
In the architecture driver, I mean.
Actually, we simply put it in the generic schedutil, the CPUFreq schedule.c, that part, which is definitely not the right thing to do. So we are just doing the study here. Yeah, eventually we might, if we want to upstream this, that's a big if, we might need to, especially in the CPUFreq schedule2.c, maybe between where you get the final frequency and the actual frequency you send to the driver, there's something in the middle that says,
So that would be the driver, right? Because
you could.
Essentially, what happens, the schedutil calls the driver, set the frequency. The driver can manipulate somehow.
Yeah, you could put in a driver.
So
The driver, you will not have any pairs.
Yes, that's true.
That in the AMU value that is reported to PELT, then your PELT signal include this.
Well, but that's kind of a workaround, I would say.
Sorry?
Because then you're affecting the whole PELT machinery, right? Or
so the PELT, it's only about tracking some cycle.
That's how I just realized that you talked about R here.
Yes.
Yeah, okay.
yeah.
In the PELT right now, we are either tracking the time, but we are also tracking APF, MPF, or the AMU cycle.
Yes, it's there for ARM, yes.
And I mean,
but I wouldn't dare to touch that.
Sorry?
I wouldn't dare to touch that design this way.
So you can, I mean, there is architecture code in the context switch path. So ARM could just store a few counters there if it so chooses.
Okay.
Yeah, that's actually what we did. So we just put it in context switch.
It has to be proper to the task, right? Because when you switch to a different task, you have different behavior.
Yeah.
So it needs to be a property.
That's also why that's exactly our next step. Yes.
So that's how whatever it comes into the picture.
Another thing, so in your test, you use the same Cortex version. Have you tried with some real big, medium, and little?
That's also our next step. Yeah.
To see if the linear regression that you're using once you run on a big or a medium or little.
So this core, the A725, that's kind of a mid core, but you're right. If you go for the prime core, well, you might face even a higher memory wall, so you might benefit even more.
Yeah, that's the point. I mean,
that would be specific per domain. right?
The moment you're bandwidth limited, bigger core is just not useful.
You might even then decide to down migrate.
That's right. If you're part of the belt, you can decide to stay on the video.
But that's a long shot from now. But so Peter, you mentioned that we could put some juicy counters there in the context switch, and then we can just reuse them. For instance, in this
I mean,
CPUFreq.
you'll have to fight Catalan and stuff, but I mean, every context switch path is per definition architecture specific. So it can just save off a few values. I mean, it already saves the stack and IP, and no, it doesn't even save the IP because you know where you are in the context switch. But yeah, it saves the stack pointer and all that stuff.
It would have to be saved just like we save the GPR.
Yeah, and then you already have a per task per architecture region for all this magic voodoo. Just add a few fields, populate them with some counter, and
It's,
happy. But
it's just, it's additional work on the hottest pass in the kernel.
Right.
It's extra memory that we can't reclaim. It's part of the.
And where does the number end, right? What is the right number? 1, 10, 20, 50.
so
memory is cheaper than other.
So yeah, so ideally you'd need a free running counter that is non-programmable by the hardware. I mean, even the x86 PMU free running counters are often a little bit programmable, so they're out.
Yeah, so-
and AMU is also a little bit configurable, so tricky.
I mean, the architecture counters appear to be read-only, so you can't mess with them unless you virtualize the whole thing. Not even considering that.
That's right.
You can mess with them from higher.
And
Yeah, you can offset them if you implement if the CPU is not shit.
so things like IPC, the absolute value is not really relevant, but you can still see whether or not it increases if you increase the frequency. So you can use it as a differential. If there is no gaining going faster, you know you've hit the ceiling.
Yeah, actually, that's
Right.
yeah, IPC. I would see it could be helpful in that way. Yes.
IPC is something that is probably easier to get free running counters for than a random magic ideal counter.
So there is one counter which is not part of this AMU, the L2 cache refill, but we have Shuvik here.
Yeah. I think.
From PMU counters, that event.
Yeah, I think at this point it's basically showing people what we are doing. Whether in the end L2 refill is the counter we choose is still, yeah, at this point we still don't know. I think it's like the stop back and mem. That's like in the linear regression mode. That is the best counter to use by a wide margin. Like the second one is the L2 refill. The first one is so good, it's like an order of magnitude more helpful than the second one.
Okay.
So even if you don't have the L2 counter, you can just use that one. It's slightly worse. It's only slightly worse.
Okay.
Yeah, so that's something we found that with that single counter, you can do quite a lot already. Yeah.
And that's because the memory stalls are just very painful. And it's an absolute number you can key on.
Yeah, and that count directly measures how many cycles you are stalled. Like that's the, yeah, that measured exactly that. So that's why it's the most helpful. Yep.
And this one is fixed. You cannot reprogram that one. You get it for free for every basically IP.
Yes. Is that the memory stall thing?
But it says that that's the object ones are all read only. So yeah, you get CPU cycles, constant frequency cycle, whatever that means. Number of instructions desired and memory stores, but that doesn't tell you where the memory subsystem. It's
It
somewhere.
tells you that you are crossing the PD, your performance domain.
Yeah, and the very.
Yeah, well,
and
all
my
this wants to
very-
know it's I'm bandwidth limited, so it might be good enough. Yeah. All right. Thank you.